Hello all, welcome back. In the previous lecture, we have seen the different atmospheric parameters and different formulae related to those parameters we have gone through. Now, in this lecture, we can solve some numerical examples and see how these equations can be utilized. First example is calculation of atmospheric variables. Let me read out the question. Estimate the vapor pressure, air pressure, relative humidity and air density at a height of 1200 meters into the atmosphere. The total pressure is equal to 101 kilopascal, air temperature is equal to 24 degrees Celsius and the dew point temperature TD is 18 degrees Celsius near the ground. The lapse rate is equal to 9 degree Celsius per kilometer, which is a constant for both T and TD, and gas constant Ra is equal to 287 joules per kilogram Kelvin, which is also a constant as a function of height. Here we are not going to consider the variability of Ra with respect to height, we will be considering it as constant for all the heights. So, let us see what are the data given to us. Delta Z, that is we are having the variables at the ground surface. Now, we need to calculate all these values, corresponding values at an elevation of 1200 meters from the ground surface. So, delta Z will be 1200 meters and Z1 is 0 on the ground surface and P1 pressure at the ground surface is 101 kilopascal and temperature at the ground surface is 24 degrees Celsius and corresponding dew point temperature is 18 degree Celsius. These data are already given to us and the lapse rate is given as 9 degrees Celsius per kilometer. That unit you need to be careful, it is per kilometers. When we are converting it into SI unit, it needs to be converted to meters. And Ra is given as 287 joules per kilogram Kelvin. These are the data which are given to us. Now, what all are the details which need to be calculated? We need to find out vapor pressure E2 at an elevation of 1200 meters, air pressure P2, relative humidity and air density at an elevation of 1200 meters from the ground surface. So, this is our atmospheric column which we have seen while deriving the expressions. We are having an area of A and at the ground surface we can consider as section 1 and at an elevation 1200 meters it is considered as section 2. So, Z1 equal to 0 and Z2 is equal to 1200 meters. Now, let us start solving the problem. Temperature at the level of 1200 meters we need to determine. Temperature, pressure, all these values at the ground level is already given to us. We are having the expression relating the temperature and pressure variability as the altitude increases. We will be making use of those expressions for finding out the corresponding values at a particular elevation into the atmosphere. Temperature at the level of 1200 meter needs to be calculated. Alpha is given to us that we are assuming to be same at the ground and at the elevation 1.2 kilometers. So, T2 can be calculated by using the lapse rate equation. T2 is equal to T1 minus alpha Z2 minus Z1. T2 is the temperature at the elevation of 1200 meters and T1 is the temperature which is given to us which is near to the ground surface. Alpha is there with us and Z2 minus Z1 is nothing but our 1200 meters. So, we will substitute all those values. T1 is 24 degrees Celsius and alpha is 9 degrees Celsius per kilometer and Z2 minus Z1 is 1.2 kilometers. we are substituting it in kilometers because our lapse rate coefficient is, lapse rate is in the unit of degree Celsius per kilometer. So, the value will be coming out to be 13.2 degree Celsius. So, the temperature at an elevation of 1200 meters is calculated to be 13.2 degree Celsius. Now, we need to calculate the dew point temperature at the elevation of 1200 meters, that is TD2. We are representing all the variables at the section 2 with a subscript 2. So, TD2, that is the dew point temperature at section 2, we can make use of the same lapse rate equation, that is given by TD1 minus alpha Z2 minus Z1. TD1 is given to us, alpha and the difference between the elevation, that is Z2 minus Z1 is known to us. That we will substitute here. TD1 is 18 and other values we will substitute in this equation, and we will get the dew point temperature to be 7.2 degrees Celsius. So, now what we have done, we have calculated the temperature, air temperature and the dew point temperature at an elevation of 1200 meters from the ground. Now, let us move on to the solution. We need to find out, first we need to find out the vapor pressure, that is the vapor pressure at an elevation of 1200 meters from the ground surface. We are having the formula, we are having the variability expressions representing the, relating the pressure at the ground surface and at a certain elevation in the atmosphere. So, vapor pressure can be calculated. We are having the equation related to saturation vapor pressure. That particular equation we have seen in the previous lecture, and corresponding to that we are having an exponential curve. That plot I am going to give here, that is we are going to plot the saturation vapor pressure versus temperature. So, the graph will be looking like this. Along the y axis we are having saturation vapor pressure, and along the x axis we are having the temperature in degree Celsius. Now, with the given data, we need to calculate the vapor pressure at an elevation of 1200 meters above the ground surface. Our temperature is 13.2 degree Celsius, right. Corresponding to 13.2 degree Celsius, what is our saturation vapor pressure? We can consider this particular point as A, and we are having a saturation vapor pressure as ES. So, A is having coordinates 13.2 comma ES, that is our, for a temperature of 13.2 we are having a saturation vapor pressure ES. But what we want to calculate here, we want to calculate the vapor pressure. In the question it is not asked about the saturation vapor pressure, it is asked to calculate the vapor pressure corresponding to a temperature of 13.2. 13.2 degrees Celsius is the temperature which we have calculated at an elevation of 1200 meters. We were having the temperature at the ground surface, and we are asked to calculate certain atmospheric parameters at an elevation of 1200 meters. For that, we have calculated the temperature and the dew point temperature by making use of the corresponding values at the ground level. We have calculated those values at an elevation of 1200 meters. So, that temperature at section 2 or at an elevation of 1200 meters is calculated to be 13.2. Corresponding to that temperature, we need to calculate the vapor pressure. It is not the saturation vapor pressure is asked in the question, we need to calculate the vapor pressure. So, here from the curve we can understand that corresponding to 13.2 degrees Celsius temperature, we are having a saturation vapor pressure of ES. And now you look at, we need the vapor pressure corresponding to this temperature. So, we are considering a point B, and corresponding to that point we are having the same temperature 13.2, but the vapor pressure is different. So, at this particular point B, we are having the temperature of 13.2 degrees Celsius and a vapor pressure of E2, that is vapor pressure at section 2. So, E2, when we consider that this particular curve, we do not have any relationship to calculate E2 other than the saturation vapor pressure. For calculating saturation vapor pressure, we are having the exponential equation, or we can make use of this graph to get the values. But what we want, we are not expecting the saturation vapor pressure for a particular temperature. We need to calculate the vapor pressure corresponding to a certain level. We know the temperature to that corresponding to that particular level. So, what we are doing, we are considering a point B which is having the same temperature, but the pressure is different. So, the pressure we are representing by E2. But this E2 is a saturation vapor pressure corresponding to another temperature, that is our dew point temperature. Dew point temperature is given to us. So, dew point temperature, this is E2, and this is a saturation vapor pressure corresponding to the dew point temperature. TD is equal to 7.2 degree Celsius. So, what we can do, the equation is valid only on the curve. Other than the curve, this equation is not valid, but the equation will be giving you saturation vapor pressure. So, we are going to calculate the saturation vapor pressure corresponding to dew point temperature. That saturation vapor pressure is the vapor pressure corresponding to the temperature T2. So, we can make use of that concept here. So, we are going to consider this point as C. So, for C we are having a temperature 7.2, but the vapor pressure is E2. E2 is saturation vapor pressure corresponding to the temperature 7.2, but corresponding to the temperature 13.2, E2 is simply vapor pressure, it is not at the saturation level. So, E2 is the saturation vapor pressure corresponding to the dew point temperature. Now, we can make use of the exponential equation which we have seen in the previous lecture. E2 is equal to 611 e to the power of 17.27 TD2 divided by 237.3 plus TD2. TD2 why we are putting there? It is corresponding to the dew point temperature. That value of dew point temperature, that is 7.2, we will substitute there. We can calculate the value E2 as 1016 Pascal. That will be 1.016 kilo Pascal. So, vapor pressure at a height of 1.2 kilometer, E2 is equal to 1.016 kilo Pascal. So, again I am repeating, the curve will be giving you saturation vapor pressure. So, for the dew point temperature, if we are making use of that particular curve, we will get a pressure, that is a saturation vapor pressure. That vapor pressure is the vapor pressure existing to particular temperature at that level. So, that is calculated to be 1.016 kilo Pascal. So, we got the value corresponding to vapor pressure. Now, let us move on to second variable, that is atmospheric pressure. How the variation of atmospheric pressure taking place as the altitude increases, we have seen. One particular nonlinear relationship we have seen with the P2 and P1. That relationship we will be making use here for calculating the pressure at section 2, that is at an elevation of 1200 meters from the ground surface. So, the relationship is given by this nonlinear relationship. P2 is a function of P1 temperature and T2 by T1 to the power of G by Ra alpha. All these variables which are on the right hand side are known to us. So, that we will substitute T1 air temperature at the ground level, that is given as 24 degrees Celsius. But we need to substitute here in this particular expression in Kelvin, because we have made use of ideal gas law. So, in that the temperature should be put in Kelvin. So, corresponding to 24 degrees Celsius, we are having a the value of 297 Kelvin. Now coming to T2 is the air temperature at a height of 1200 meters that we have calculated already by using the Labstrade equation. It is 13.2 degrees Celsius equivalent to 286.2 Kelvin. And we are going to substitute in this particular equation. So, after substituting that, we will get the value corresponding to pressure at atmospheric pressure at section 2 or at an elevation of 1200 meters. One thing you need to be very careful here, we are having Ra multiplied by, that is P1 multiplied by T2 divided by T1 to the power of G divided by Ra alpha. So, Ra we know the value is 287, alpha should be in SI unit. Alpha, what is the unit of alpha? Degrees Celsius per kilometer, that is 9 degrees Celsius per kilometer. That needs to be converted to SI unit, that is why we are multiplying it by 10 to the power of minus 3 here. So, this need to be taken care, otherwise you will not be getting the correct answer. So, P2 can be calculated to be 87.75 kilopascal. So, now we have calculated the vapor pressure and atmospheric pressure at the level of 1200 meters above the ground surface. Next is relative humidity. We need to calculate the relative humidity. We know the relationship for the calculation of relative humidity. What is the expression for relative humidity? Relative humidity at section 2 is given by E by Es at section 2, that is we are denoting by the subscript E2, E2 divided by Es2. We are having the value corresponding to E2. Now, we need to calculate the saturation vapor pressure at section 2 corresponding to that particular temperature. That we will make use of our saturation vapor pressure curve equation, and E2 is the value which we have calculated already. It is 1016 Pascal, and Es2 saturation vapor pressure value we have not calculated at the level of 1200 meters, that we need to calculate. Same curve we will be using, Es versus temperature curve. In this we need to calculate the vapor pressure, that is our saturation vapor pressure corresponding to a temperature of 13.2 degrees Celsius. Our temperature at level 1200 meters is 13.2. Corresponding to that 13.2, what will be the saturation vapor pressure that we need to calculate? This is Es, and Es can be calculated by using the exponential relationship. Here we will be substituting T2, because corresponding to the temperature T2, what will be the saturation vapor pressure, that is what we need now. So, Es2 is calculated, T2 is 13.2 degrees Celsius, that we will substitute here and we will get the value corresponding to Es2. You can calculate it, it will be coming out to be 1518 pascals. So, now we are having the value corresponding to E2 is there, Es2 is there, we can substitute in the given expression for relative humidity. So, when we substitute, we will get the value of relative humidity at section 2 as 0.669. In percentage, it will be 66.9 percentage. So, this is the relative humidity at a level of 1200 meters above the ground surface corresponding to the data given to us. Now, we need to calculate the air density at section 2. Air density calculation we will be making use of ideal gas law. We know P is equal to rho RT. So, here it is air, that is by rho A RT. It is corresponding to section 2, then it will be P2 rho A2 RA T2. RA we are initially itself I told you, RA we are assuming the same all throughout the elevation for this problem. So, P2 is equal to rho A2 RA T2. T2 is known to us, RA is known to us. and P2 is also known to us. So, we can calculate rho A2. Rho A2 is equal to P2 divided by RA T2. We are substituting the corresponding values. Here this is based on ideal gas law. So, the temperature should be in Kelvin. That is why we are converting the degree Celsius temperature in degree Celsius to Kelvin. It can be calculated as 1.0683 kilogram per meter cube. Air density at section 2 is 1.0683 kilogram per meter cube. These are the variables which are asked to calculate. We have calculated the vapor pressure at section 2, temperatures at section 2, that is the dew point temperature and the temperature, and the vapor pressure, then atmospheric pressure, relative humidity and air density. So, whatever formula we have seen in the previous lecture were made use here for calculating these atmospheric variables. So, you need to be very careful about units. Certain places we are putting the temperature in Kelvin, at certain places we are putting it in degree Celsius. So, when ideal gas law is involved, the temperature should be in Kelvin. Now, let us move on to second problem, that is related to the quantification of precipitable water. We have derived the equation how much will be the quantity mass of water vapor present in the atmospheric column, which is responsible for the precipitation which we are experiencing on the ground. So, that we will calculate that. How it can be calculated we will understand by making use of this numerical example. The question is, estimate the amount of precipitable water in a saturated air column in millimeters of water 12 km high above 1 meter square of ground surface. The surface pressure is 101.3 kilopascal. The surface air temperature is 28 degrees Celsius and the lapse rate is 6.5 degree Celsius per kilometer. So, we have given certain data corresponding to the ground surface temperature, pressure and the lapse rate. Lapse rate value is there, so that we can calculate the temperature corresponding to any elevation. And if the pressure and temperature at the ground surface is the different elevations, we can calculate the corresponding values. What we need to calculate? We need to calculate the amount of precipitable water in the atmospheric column. Dimension of the atmospheric column is given to you, that is it is 12 km high above the ground surface and the area is considered to be 1 meter square. So, we will start solving the problem. Data given are Z is equal to 12 km, ground surface level is 0 and at an elevation of 12 km. So, our Z we can consider to be 12 km and area is equal to 1 meter square and surface pressure is given to you 101.3 kilopascal and surface temperature is 28 degrees Celsius. Lapse rate is also given to you, that is 6.5 degrees Celsius per kilometer. Now, making use of these data, we need to calculate the amount of precipitable water in the saturated air column in terms of millimeters of water. That is, you will be getting in kilogram, that needs to be converted into millimeters of water. That is, later on we will be making the conversion to millimeters of length unit of water. So, what we will be doing in this, if you remember the expression carefully, we were having the integral equation that we have discretized and average values were taken. So, at that time itself I have mentioned at different level, at a certain elevation if we are calculating, we will be dividing the entire reach into small reaches. The depth of the reach is considered to be very small, so that there will not be much variability in these atmospheric parameters. We can average out these parameters. So, let us see how it is done. What we will do, we will divide the entire, we are having 12 kilometer reach. We need to calculate the total amount of precipitable water present in an atmospheric column which is having a depth of 12 kilometers. What we will do? We will divide the entire 12 kilometers into 6 reaches, that is each reach will be having 2 kilometers. So, we will see the values corresponding to initial 0 to 2 kilometer, how much is the total precipitable water. In the similar way, we will repeat for the entire 12 kilometer reach, 2 kilometer, that way up to 12 kilometer reach, and finally we will add up all these quantities to get the total amount of precipitable water, that is the water vapor present in the 12 kilometer height atmospheric column. So, let the increment in elevation delta Z be 2 kilometer. It is up to you. You can consider 500 meters, or you can consider 1000 meters, and you can consider 3000 meters depending on the total depth given to you. But the thing is that the depth should not be too high. To 12,000 as such entire depth, if we are considering together the values, we cannot average out. For averaging out, we will consider different strip depth to be very small. That is why I have divided into 6 strips which are having 200 meter depth. So, for the first increment, Z1 equal to 0 meter, that is at the ground level, and Z2 is 2000 meters. So, we have given in the question, it is given T1 is equal to 28 degrees Celsius, corresponding value in Kelvin will be 301 Kelvin. Now, at Z2, what is our Z2? Z2 is 2000 meters above the ground surface. So, at Z2 we need to calculate temperature T2. We are having the lapse rate coefficient alpha is equal to 6.5 degree Celsius per kilometer. When it is converted in meters, it will be 0.0065 degrees Celsius per meter. So, T2 can be calculated by using the lapse rate equation. T2 is equal to T1 minus alpha Z2 minus Z1. So, we will substitute the corresponding values here. T2 is equal to 28 minus 0.0065 multiplied by 2000. So, it will be coming out to be 15 degrees Celsius, and that value in Kelvin is 288 Kelvin. So, we got the temperature, ground level values are given to us, and temperature at a level of 2000 meters we have calculated. In the similar way, we need to calculate at 4000 meters, 6000, that way up to 12,000 meters we need to calculate these values. Now, the air pressure at 2000 meter. Air pressure P2 is given by this particular expression. How the pressure is varying from the ground as the altitude increases from the ground surface, we know the expression. That particular expression we will use for calculating the air pressure. So, that is given by this equation, and here the gas constant is given to, we know the gas constant, that is 287 joules per kilogram Kelvin. So, we can substitute the values here, that is P1 T2 by T1 to the power of this ratio, that is coming out to be 5.26, and after that we are going to substitute for T2, T1 and P1. So, the value can be calculated to be 80.31 kilopascal. So, the air pressure at an elevation of 2000 meter is calculated as 80.31 kilopascal. Now, we need to calculate the air density. We can calculate the air density at the ground surface, that is rho A1 is equal to P by RAT. Here we are making use of the ideal gas law, the temperature should be in Kelvin. So, air density at the ground surface, sometimes it will be given to you, or else with the known parameters you may have to calculate it. Rho A1 can be calculated by using the given values. It is calculated as 1.173 kilogram per meter cube. So, air density at the ground surface is calculated to be 1.173. So, now what we want? We want the air density at an elevation of 2000 meters. Rho A2 is P by, same expression we are using. So, we need to make use of P at the section 2, that is at 2000 meters. that we have calculated 80.31 into 10 to the power of 3 divided by RAT, 287 multiplied by 288. It will be coming out to be 0.9716 kilogram per meter cube. So, you can understand air density rho A1 and rho A2, look at the values. At the ground surface it is 1.173 kilogram per meter cube, and at an elevation of 2000 meters it is lighter, that is it is coming out to be 0.9716 kilogram per meter cube. So, as we go to higher elevation, the density reduces. Now, average density over 2 kilometer increment, 2000 meter increment, that integral equation we have discretized, and we are calculating the average value corresponding to that to make the expression simple. So, the average value of air density is 1.0723 kilogram per meter cube. Now, we can calculate the saturation vapor pressure. The saturated vapor pressure at ground surface we can calculate by using the exponential relationship with the temperature and the saturation vapor pressure. That is, at ground surface we will be making use of the temperature at the ground surface, and it is calculated to be 3.781 kilopascal. Temperature is 28 degree Celsius. Now, saturated vapor pressure at 2000 meters, the temperature is 15 degrees Celsius at delta Z is equal to 2000 meter. So, when we substitute 15 degrees Celsius in this particular equation, we will get the vapor pressure, saturation vapor pressure to be 1.71 kilopascal at an elevation of 2000 meters above the ground surface. Now, what we want? We want to calculate the specific humidity. Specific humidity at the ground surface we will calculate first, then we will go to an elevation of 2000 meters, then we will average out the values. So, QV1 is given by 0.622 E by P. This expression we have seen when we were talking about the water vapor dynamics topic. Here we will substitute the values corresponding to vapor pressure and the total pressure, we will get QV1. So, those values are 0.622 multiplied by 3.781 divided by 101.3. It will be coming out to be 0.02322 kilogram per kilogram. It is unitless, dimensionless. It is specific humidity, right. Now, specific humidity at an elevation of 2000 meter from the ground surface we need to calculate. Same expression we will use, and it is calculated to be 0.01324 kilogram per kilogram. That is, the vapor pressure at an elevation of 2000 meters is 1.71 and the atmospheric pressure is calculated to be 80.31. So, now we can average out this value to get the average value of specific humidity at 2 kilometer increment at an elevation of, that is QV bar, it is coming out to be 0.01823. So, now all the values required for calculating the total amount of precipitable water in an atmospheric column is there with us. Now, we can see the formula. The mass of precipitable water in the first 2 kilometer increment is given by, the formula is same for all the increments. So, the formula which we have derived is written over here. Delta MP is equal to QV bar multiplied by rho A bar multiplied by A delta Z. We have calculated the values corresponding to QV bar, rho A bar, area is given to us, that is 1 meter square, delta Z is we are considering an increment of 2000 meters. We can substitute the corresponding values over here, and the value corresponding to total mass of precipitable water is 39.096 kilogram. mass of precipitable water in the first 2 kilometer increment is 39.096 kilogram. The same step has to be repeated for all the increments, all the 2 kilometer reaches until we reach 12 kilometer, entire 12 kilometer atmospheric column. So, that I am not showing here, that has been calculated in a Excel spreadsheet. We have calculated the mass of precipitable water. Now, we need to do the same procedure for next increment, next 2000 meters up to until we reach an elevation of 12,000 meters. So, that has been shown here. I have calculated by using an Excel template, and ground level calculation we have seen step by step. Ground level we were having a temperature of 28 degrees Celsius, and as the elevation increases the temperature changed up to -50. That has been converted into Kelvin because ideal gas law is involved in some of the formulae. And for the calculation purpose, I have made 2 columns, which is of T2 by T1 and to the power of G by Ra alpha for calculating the air pressure. So, air pressure is calculated by using the pressure relationship which we have derived for getting the pressure at higher altitude. So, that way we got P2 for all the incremental elevations. Air density again by making use of the ideal gas law for different incremental elevation we have calculated, and vapor pressure by making use of the saturation vapor pressure curve we have calculated. E is there, P is there, so we can calculate the specific humidity for different incremental depths. After that we have calculated the average value of QV bar 0 to 2000. What is the average value coming? It is 0.018 corresponding to specific humidity and also air density. We have calculated the average values. Same step is repeated for other incremental elevations also. So, we got these values, and finally for each increment of delta Z we have calculated the mass of water vapor, precipitable water present in the increment. Each increment we have calculated up to 12,000 meters, and total value was calculated to be 68.475 kilogram. And the same thing we have, the percentage of total mass for each increment is calculated by 39.1 divided by 68.475 into 100. You will get the percentage of total masses at each increment. That is also calculated. But in the question it is asked, here we have calculated delta MP and total MP in kilogram. In the question it is asked to calculate in meters or millimeters of water. So, the total mass of precipitable water in the column was calculated to be 68.475, actually it is 475 kilogram, and the equivalent liquid water will be MP divided by rho WA. How it will be coming? You know, mass is equal to density multiplied by volume, right. So, rho into A into H. So, we need to get the depth of water, that is we need the value corresponding to H, that is nothing but mass divided by rho into A. Rho here in this case is rho W, density of water, that is what is written over here, mass of precipitable water divided by rho W A. So, mass of precipitable water is 68.475 we have calculated, and rho W we are taking 1000 kilogram per meter cube, and area is 1 meter square. So, it will be calculated as 0.068475 meters. So, when we convert it into millimeters, it will be 68.48 millimeters. So, the equivalent corresponding to a mass of 68.475 kilogram, we are getting an equivalent water around 68.48 millimeters. So, in any unit it is if it is asked in the question, you can calculate that. So, here it is 68.48 millimeter for these given atmospheric parameters. So, here I am winding up now. Thank you.